Alright, so if we take a look at number 9, here we've got cobalt 60. It's an isotope of cobalt that's produced during nuclear reactions. And a consequence of this is that it produces gamma rays type of radiation that has high frequency, therefore high energy. And they use this to treat certain types of cancers. They use it as far as radiation goes. So if the wavelength of gamma radiation from cobalt 60 is 1 times 10 to the negative third nanometers, calculate the energy of this photon, of this radiation. Well, since we're dealing with energy, it's going to be nice to kind of see what equation we'll use. And the equation that will probably help us there is energy is equal to h nu. And here we're given a frequency. I'm sorry, not a frequency, but a wavelength, a distance. This is our wavelength here. So we're going to use an equation that deals with wavelength as well. So we've got our C is equal to lambda nu. And this deals with wavelength. We've got nu in both of these. So let's just do a little algebra. Let's rearrange this to get what C is equal. I'm sorry, what nu is equal to. So let's get this all by itself. If you remember the really bad joke, what's nu? C over lambda. But if we just divide each side by lambda, that's going to cancel these guys out. And we're going to end up with nu is equal to C over lambda, speed of light over our wavelength. We've got nu here, and we've got nu here, so we're just going to take this and substitute it in. So now we're going to get a new equation. E is equal to h times c over lambda. We know what h is. That's Planck's constant. 6.626 times 10 to the negative 34 joules seconds. And we know what our speed of light is. That's 3.0 times 10 to the 8th meters per second. And we also know what our wavelength is. Our wavelength is 1 times 10 to the negative third nanometers. Oh, nanometers there, but meters here. They don't jive. So we got to convert one into the other. So I'm going to use the conversion factor that we saw on the first page, the last problem on the first page, and we're going to convert nanometers into meters. And our conversion factor says that 1 nanometer is 1 times 10 to the negative 9th meters. So if I do this, we're just going to end up 1 times 10 to the negative 12th meters is our wavelength. So let's just plug that in to lambda. So 1 times 10 to the negative 12th. And then all I need to do is just plug these into my calculator. I forgot a unit there. That's going to be meters. Alright, so if I do this, if I end up with this, I've got my work all over the place, so sorry about that. I end up with 1.99 times 10 to the negative 13. Well, what are my units going to be? Let's see. I've got a meter down below, and I've got a meter up here, so our meters are going to cancel. I also have a second here, but I also have a per second here, so a second per second. That's going to be canceling those out. And all we're left with is joules. And luckily for us, joules are a measurement of, or a unit for energy. So the amount of energy in this photon is 1.99 times 10 to the negative 13 joules. Not a lot, but if this is just the energy of one photon, well, anytime a source of radiation comes on, you're getting tens of billions of photons, so this adds up pretty quickly. So this is pretty high energy. And that's it. That's how you do one of these.